Yeah, we're good. You don't need a bell. All right.
Jacob, I moved your bag behind the desk. Your bag was up there, I moved behind the desk. Do we have a Facebook? No. Let me toss this. Jacob knows. Yeah, we'll watch it. Hey everyone. Oh, sorry. Hey everyone, let's settle down and let's get started with the presentation section of the event. Okay. Can we shut down, close the back doors, or the front doors, please? Okay. Thank you so much. Thank you to everyone for attending Berkeley Space Symposium 2025. I'd love to share a few minutes about the organization that brought you this event, New Space at Berkeley. New Space at Berkeley is an organization that focuses on building a hub for everything space at UC Berkeley. The reason this organization was created was to tackle two main issues. There was a lack of awareness among students about space opportunities on the Berkeley campus, as well as students only believed that there was only engineering opportunities in space, and there is much more to that within the space industry. To start off, the way that we tried to implement and solve this within the organization is through three clear verticals. Our first vertical is the education vertical, where we teach about the new space economy and new space entrepreneurship. The second key vertical is the space policy vertical, where we inform legislators about space policy and write white papers about rising topics in the industry. And the third key vertical is our career development vertical that brings events such as Berkeley Space Symposium to students and industry across the Bay Area. To talk about first, we'll talk about the New Space Education vertical. We run a two-semester decal called the New Space Economy and Entrepreneurship. Through this course, we work with industry professionals year-round and learning more on the technical aspects while also learning the space policy, legislation, as well as all aspects of building a space startup as we are in Silicon Valley. It is a great opportunity to connect with industry professionals, and students in the past have been able to present at company headquarters such as NASA Ames, as seen in the image above. We would like to thank our current partners that we have as industry partners this year: Ursa Major, Astroscale, and US Space. We'd love to thank them for being industry partners on our projects, and if you'd like to learn more about what the work they do, they will be tabling outside. The next key vertical that we'd love to discuss about is our events vertical. We host space company site tours, such as visiting Longshot Space's Space Cannon in the Bay Area, attending space conferences like the Space Symposium, as well as SmallSat Symposium across the United States, as well as hosting community and industry events such as Berkeley Space Symposium. And in general, the organization is a great way for students to find a place within the industry. We've had students placed within NASA, the government, the House of Representatives, SpaceX, as well as within finance. It is a great way to expand your knowledge, as well as find a place that really fits you well within the Berkeley campus. I'd like to now hand it off If you're interested in being part of the organization, the left QR code is the organization application. The right QR code is the decal application, where it's a student course run for 2 semesters and 2 units, as I had mentioned. Feel free to scan these QR codes. We'll leave them up for a few seconds. And there's also on the New Space at Berkeley website. I'd like to now hand it off to Chris Kemp, the CEO and co-founder of Astra. From being the first CTO of NASA Ames, he has had a remarkable journey within the space industry, and he would love to share a few words about his journey and the company. Thank you.
Cool. Hey, everybody. Good to be here. What I really am excited about is just being here where you guys do so much stuff. You build hardware. I think you guys were founded, I think, back in the 1950s. Since then, I think you guys have done about 24 rockets. You guys have done like over 100 satellites. I think the coolest satellite ever, just coming back from Burning Man, in 1992, you guys did the Ultraviolet Explorer satellite and determined that the universe actually glows in ultraviolet light. I love things that glow in ultraviolet light, so saw a lot of that last week. This is something that really makes Astra Astra. So we started out in a garage in San Francisco, and we built hardware, just like you guys do. And the hardware, one thing led to another thing, and the more you build, the more you learn, because you can do a lot of analysis and design stuff, but until you actually build hardware, you can't calibrate the analysis and the designs and make real progress. A lot of what you do just doesn't map to what you thought it would do. And so until you actually build hardware and test hardware, you're just not going to move very quickly. So I think what we're starting to see in the space industry is two very different approaches to innovation. An approach where I call it like the Blue Origin NASA approach, where you spend tens of billions of dollars, and in 20 or 30 years, you build a rocket and it works the first time. And this is super important if what you're trying to optimize for is it works the first time. And for a program run by a nation state or a billionaire that doesn't want to have a rocket blow up, this is prudent, but it does take decades and cost tens of billions of dollars for you to do the analysis and the testing leading up to the event where you get a success the first time. Very impressive, very expensive. Obviously, that wasn't the path we chose. It's not the path SpaceX chooses after 10 Starships are, in a very exciting fashion, dismantling themselves on their way to orbit. But they're learning very quickly, right? And so anyway, I think that's kind of where I'll start this. Back in late 2016, early 2017, we were in a garage in Soma that was about 1,200 square feet. And this is Dr. Adam London. He is the brains of the operation. He did his undergrad, master's, and PhD at not Berkeley, but at MIT, where he was very focused on very theoretical things. Like he built a rocket engine that was the size of your thumbnail, that was literally photolithographically etched on a silicon wafer, and all the valves internally were MEMS. And if you took thousands of these little things and glued them together, you'd have like a Star Wars-like engine, where you have a hypothetically very efficient engine, but you built them in the lab, and they kept exploding, because apparently silicon is a pretty, dusty thing to work with when you start to apply pressure to it and things like that. So, Adam and I teamed up, and the first thing I asked Adam was, well, like, how do we make this less theoretical? Like making really small rockets is one thing, but is there a business case that is different than, say, a rocket lab, because they were well underway, SpaceX well underway? Is there something different that we can do? And so the big idea that we had in this garage was, well, what if you just make thousands of rockets? There's actually another academic paper you can find still on the web today on the Fermilab website called "A Rocket a Day Makes High Cost Go Away." And it was written back in, I think, 1992 as well, when you guys did that cool ultraviolet satellite. And the thesis was that the reason why rockets are so expensive is because you don't make many of them, right? And so all of your fixed costs are amortized over a relatively small number of vehicles. And so this drives towards a thinking around, well, if you're going to make a small number of something, you better make it reusable, because why throw away an airplane every time you fly it? It sounds pretty logical. So this kind of drove this idea around the rockets must be reusable, and rockets must be very large as well, because if it's, if you're going to maximize the amount of payload you're trying to reach to orbit, the mass fraction of the rocket needs to be as large as possible. And so you've got this school of thought around, well, let's just make the largest rocket ever and make it reusable, which is the SpaceX approach, and I think the industry is going to. So our approach was always the opposite of that. It's, if you take a soda can, soda cans, I think we make about 1 billion of them every day out of aluminum. Aluminum is basically free. And if you can figure out a way to take aluminum and turn it into, a rocket's basically a big cylinder with some domes on it and an engine. And if you look at an engine, a rocket engine in some ways is simpler than an internal combustion engine. It doesn't have, a bunch of pistons and moving parts and magnetos, and it's just a combustion chamber. If you, depending on the engine cycle, you can actually tap off the combustion gases into a turbine. You have a single turbine that can turn 2 pumps. It actually has fewer moving parts by a significant margin than an internal combustion engine. So you can get back to the, well, if you just build a lot of them, maybe the cost can come down. And so the basic idea in that garage was, let's do the math. Let's just look at what the BOM cost of a rocket would be if you made 500 of them, as suggested by this paper, "A Rocket a Day Makes High Cost Go Away." And so that's how things got started. So about 1.5 years after we founded the company, that picture was taken. That was not generated by AI. What's super cool about this picture, among other things, there's a rocket firing with the Salesforce tower behind it, but it gives you the timestamp. This little area right here is where they filmed The Matrix. That little black thing, that's the highway scene where they were kind of jumping around between cars and things like that. And you can still see, I think they finally put dirt on top of this, but there was, you could see from satellite images the soot on the asphalt that we charred there. that was rocket 1. Actually, that's rocket 2.0. Anyway, so that whole system we could transport out to the airfield and test about a mile from our office. And this is all about 5 miles from here, just to give you a sense of what's going on in your backyard. We timestamp pretty quickly after that demonstrated that we could build an orbital vehicle. And that image was taken on December 15th of 2020. Again, the company was founded more or less January of 2017 is when we actually got going. So the business was incorporated on October 1st, 2016. So pretty quickly, putting that back in the kind of framework of other companies, we basically did this in just over 4 years. Falcon 1 at SpaceX took about 8, 7.5. And then other companies. So how did we do this quickly? Well, there was a movie about it. We were not afraid to build rockets and test them, just like SpaceX is doing the Starships. Like the more you're able to build hardware, collect data, and iterate on the design, the better. And so this led to a mistake. That's fun. So yeah, so this was 2021. The next year we got to orbit, and we're like, wow, this is great. Let's go public. Virgin Orbit had gone public. Rocket Lab was going public. Planet was going public. A huge amount of capital in capital markets had been moved into these things called SPACs. I didn't know what a SPAC was, but it sounded, like we've got to raise some money. The thesis of the business was we've got to build a rocket factory, right? We're not building a rocket, we're building 1,000 rockets. So I need to raise a bunch of money to build a rocket factory because that's the whole point of the company. So let's go public. And anyway, that was the day the stock traded at its highest value. The next day it was lower. We would launch a rocket, it would work, it would go lower, the rocket would blow up, it would go lower. Nothing we did, no sale we announced, basically every piece of news that came out of this company, the stock went lower. And that got to the point where, it just didn't work out, but I'll get to that in a second. What we were able to do is we were able to take the $500 million we raised in that public offering to go build the factory that we needed to mass produce the rocket. And that was key. So this is a building which the only thing that we painted since 1983 was the black little front of it. So every dollar, every wall socket, every Ethernet port, every workbench in this building was purchased, and literally it was a shell of a building with lead paint just falling off the ceiling. We literally turned every penny into the means of production to build a rocket a day. And so that kind of looks like that now. It took a bit of time to build that out, like 2 years. But if you drive down the street, you can actually see a larger than SpaceX Hawthorne facility manufacturing plant that can actually churn out 2 rocket stages per day with one more of these little, you need 2 of these to do that, about $1 million. Here's a little fly through, it's kind of fun. That's the rocket production line there. So we basically take a coil of aluminum that costs about $20,000 that can make 3 rockets. We uncoil it, we flatten it, we laser cut it, we recoil it, we friction stir weld it, and then there's a circumferential welder that builds the cylinders of the rocket. So the whole concept is, you put in aluminum on one side of the building and then rockets come out of the other side of the building. And there's rocket 4, most of the mechanisms, engines, valves, all the electronics, all the software, it's all made in that building. So this is kind of like a gigafactory to Tesla is a rocket factory to Astra. And so you could put more rocket factories in other places and you can make rockets in a lot of places. Why do you make rockets? You don't make rockets because they're fun, they are fun, but you make rockets because they're delivery trucks to space. And so if you're going public and you're raising billions of dollars, then you need a business plan, which is not just we're going to make delivery trucks. Just like SpaceX is currently valued at $400 billion because of Starlink, like we wanted to have a satellite that would justify all the rockets we were planning on building so we could build a vertically integrated space platform. I'm not going to get too deep into that, but it's a whole interesting topic. First thing we did was we bought a Hall effect thruster company, because to build a satellite, you need like 4 things. You need propulsion, you need payload, typically a phased array antenna, optical interconnects. You need a solar array, and then you basically need the, what am I missing? The bus itself. So this was a key element of the efficiency of the constellation. So we went shopping, and we found the most efficient engine, because if we're going to have a small rocket, you need to get the most bang for the buck out of these satellites, because the satellites are going to be smaller than what you might launch on a Starship. So we found this company down in Mountain View, led by a guy named Mike Cassidy. Super efficient engine, has like 1,400 seconds of ISP. Perfect for putting about a 500-kilogram satellite in orbit and keeping it there for about 5 years, powered by krypton or argon. It had never worked yet, but we paid $150 million for the company because, hey, we just raised a bunch of money. This business actually kept Astra alive for the past few years. So when things got crazy, we were working on this rocket, and we had bought this spacecraft engine business. And then as we were trying to make that work, things went a little sideways. And I think we lost about $1 billion that day. I looked at that and I'm like, it's annoying. So at that point, things got a little, but we were working on this rocket, and the rocket was very important. I decided, let's sell the satellite engines. So let's see if we could, because the engines had started to work. We had this big SDA constellation going up. We sold hundreds of these satellite engines for about $500,000 a piece. So we had about $100 million of orders for satellite engines. And as a public company, this is revenue. This is good. Let's see if that'll work. It didn't work. Basically, there was a point in that journey where the market cap of the company was like $50 million or something like that. And so obviously, I'm the worst public company CEO ever. So I met with the board, called a little board meeting. I'm the chairman, so all my fault, obviously. I said, okay, board, you should fire me because this is just totally not working out, or you should sell the company. And I want to help you do whatever you can do for our shareholders that have invested in this company, like whatever the best outcome is for them, we should totally do that. And I'm going to fully empower you as the independent members of the board to figure this out. You should hire new investment bankers. You should hire new advisors, because obviously the ones that I've hired are crap. Here's an offer to buy the company, which was a bit of an interesting board meeting. I also told them that they could fire me, but I couldn't fire them. So they were totally independent and safe for me, even though I had a lot of power over the situation. But they should go and do that. So I helped them attempt to find a buyer for Astra. And what happened there, this is about 2022, 2023, Virgin Orbit went bankrupt. And no one bought them. No one even bought their assets. And so we're out there trying to sell Astra to Rocket Lab, to everybody. But no one wanted to buy it because, you have Richard Branson's thing where you have a 747 drop in a rocket and you just get knighted. They're not buying that. Why would you buy Astra, right? And so we literally could not find a buyer other than me and Adam for this company that was once valued at billions of dollars. And so we bought the company back from shareholders so we could finish what we started. The lesson there is if you've got a team of people and you are working on something important and you have customers and you have a bunch of engineers and employees that are not giving up on you, well, don't give up on them, right? Don't give up on your customers. Don't give up on your employees, whether you're public or private or what the thing is. These are all, name one satellite company that hasn't gone bankrupt. Name one airline that hasn't gone bankrupt about 3 times. You won't find one. So in this industry, this is really hard stuff. And if you're a leader or if you're involved in a company, just see it through, right? The thing that matters is this rocket began its life 5 years ago with a tremendous amount of hard-fought lessons learned from rockets that flew sideways, rockets that did all sorts of things. If you can keep that together, that's the only way to succeed. Look at SpaceX. It took them a failed flight, rocket, the third Falcon 1 flight, Elon had literally, he was broke. Like he literally borrowed money from his friends to get that across the line. And if he had not done that, SpaceX wouldn't be. And it was ultimately NASA, while I was there, they gave him $500 million that he loaned to Tesla that saved Tesla. So the lesson here is just don't give up on this stuff because it's hard. So that's, the other lesson is product market fit's a bitch. So we thought in 2017 that satellites would largely be like Planet Labs' Dove satellites. The dominant form factor for satellites moved from these CubeSats to 500-kilogram communication satellites. So if you're building a rocket and you're seeing thousands of Kuiper satellites and SDA satellites and Telesat satellites and Iris Squareds, you go look at what's out there. That little rocket was too small, and so is Electron. So the problem is if you can only throw a few hundred kilograms, your TAM, your addressable market, is basically insignificant. Right? So it costs the same-ish to build the small thing as the big thing. So just build the thing that addresses the market. The problem is when you're talking about a rocket, That's a complete redesign. You literally have to start over. There is almost not a single part, maybe the video camera, that isn't, every valve is sized differently. Every run line is sized differently. The entire you basically have to, from systems engineering perspective, you have to literally start from scratch. It's a do-over. And so all you take with you is the lessons you've learned and the experience you have making all the mistakes you made to get you there. So anyway, that's what we've been up to. I want to take one thing that we did from the very beginning that I really liked was, why do we need to exist? Right? There's plenty of rockets out there. Eric Schmidt just took over relativity. That's cool. Rockets are hard. He'll figure that out. But like, he's going to go build a rocket that is twice as big as Falcon 9. Okay? So you've got Blue Origin, you've got the Starship, you've got Relativity, you've got Ariane 6, you've got Vulcan, lots of big, and you've got Neutron, lots of big rockets out there, lots of big reusable rockets out there. What we haven't seen is we have not seen a completely mobile tactical rocket. So what if, here's a big idea, what if you could put a dozen drones in that rocket? What if you could go put those rockets anywhere, in hundreds of locations? I just saw yesterday, the Lockheed Martin Missiles and Defense Group got a $9.8 billion order for 1,780 Patriot missiles over the next 2 years. Okay. Patriot missiles are used when you have like Houthis lobbying things into Israel and you need to like intercept things. They're 10-inch diameter, 16-foot long, solid rocket missiles, basically, for $4.7 million a piece. They sold those. $10 billion contract, Patriot missiles. So Patriot missiles, that's a $100 billion program. There are about 1,400 Patriot missile launchers organized in batteries of 48 launchers in about 130 locations in 18 different countries. Why do I know this? I think it's interesting. Because if there are Patriot missile systems in 18 different countries, how many space agencies exist in the world? 100. How many sovereign nations can actually get to orbit? 6. So there's a total addressable market of like 75 space agencies that would love to be able to get to space. How are they going to do it? China, India, or Astra? This is the way you do it, because I can pack these rockets up and the spaceport into shipping containers, and I can send it. We have a DoD contract already to do the first launch out of Australia, the UK. Every European attempt to build a small rocket has, up until this point, failed. There is a global market to, just like in the early part of the last century, use American aerospace technology to transform the aviation industry. We can transform the space industry, but you're not going to do it with the Starship, right? Because the international airport starts out as a dirt airstrip. When you land at the Oakland airport down the street, this is where Amelia Earhart landed. There's an old building there. You take a small airplane and you land it on a dirt airfield. We can launch this rocket from a dirt strip. The last launch that we did out of Cape Canaveral, which they told us it would take 2 years to do, it took us 6 months. First Part 450 license was done on a launch pad that did not have electricity. So we showed up with our containers, we set up, and we did a launch in 6 days. From arriving at the site without electricity, and we had a network connection. Now we don't need it because there's Starlink. So we could literally go and airlift this system onto an island and launch it. I like to joke we could do it from a Walmart parking lot. Walmart doesn't like that. But, I mean, you don't want to crash on a Walmart. But the idea is, if you could put these portable mobile spaceports in a dozen countries, if you could have millions or thousands or hundreds of thousands of Anduril drones in thousands of rockets, in shipping containers, in hundreds of locations, in dozens of countries, why the hell do you need 850 military bases all around the world that cost the better part of $1 trillion to operate? If you look at the $1 trillion defense budget, about $800 billion is O&M, which is code for that's what we pay to run the machine. It's not hardware. It's just we're spending $800 billion of your money every year to operate hundreds of military bases all around the world, so a bunch of Navy SEALs can put a bunch of drones next to a border that can fly to do a mission. Rockets, AI, and drones are the future of defense, full stop. And so if you can put drones and rockets, and you can put rockets anywhere, why would you, like right now we have a defense posture of, if space is so important, if GPS is so important, if communications and Earth observation is so important, who cares if you have thousands of satellites if you only have 2 spaceports? You know, the adversary just has to take out 2 locations, and they shut America out of space. That is a vulnerability which will actually create a war. But if the adversary knows that you can replace any satellite from anywhere, it's actually the most powerful deterrent for World War III ever. So if you go back to the thesis around the whole arms race with the Soviet Union, there is a new arms race, and it's about rockets, AI, and drones. And whoever can have a more resilient infrastructure in space, if you can achieve that, you can achieve peace. Because you basically become impossible to attack. You can't disable what you can't see. So our rockets will always fit in shipping containers. Our spaceports will always fit in shipping containers, and we'll put little Walmart logos on them and Amazon logos. And so you don't know whether it's the Amazon delivery truck, you don't know whether it's an Amazon distribution center or a rocket factory. Because what's going on is, you know, in space, what do you see? So there's a future here where this kind of stuff is becoming increasingly important. There's our rocket being loaded into a C-130. We've only ever launched this way. This isn't hypothetical. Every time we've ever launched, we've done a hot fire test here in California, and then we've shipped the system to wherever it's launched from. Cool, okay. Other things going on. So yesterday, Al Weston's here, one of my heroes. I have the opportunity to work with him now. Can't say enough about Al. Al and I worked together at NASA Ames. He ran all the programs. He discovered water ice on the moon, crashed the spacecraft, bombed the moon, worked on a bunch of missile defense stuff, made a lot of things that went boom. Generally, the Aegis interceptors that are protecting us from things that are attacking our bases was his program at the DoD. Kind of cool. But this is his engine. So this is we have a new rocket engine. There was a company called Firefly. They went public. And we bought the engine from them, and it was garbage. So we literally couldn't get the same engine twice from them, and none of them matched the CAD. And if you're in engineering, you know that that just doesn't work. So we had to basically start from scratch with this engine. So we built a completely new combustion chamber out of a new copper alloy called GR-COP. And yesterday, that engine fired for the first time, and we are planning on trying to fire it again here in the next few days. Super cool engine. It's, I believe, the largest 3D printed engine. It's printed in 2 parts. It uses some of the heritage we developed around welding the engine. So it's basically printed inside of itself in a printer bed, and then it's welded together, so it stands about that tall. And it's a super cool engine, and we're going to have 2 of these powering Rocket 4, producing just under 50,000 pounds of thrust, so we'll be able to throw about a ton to orbit with the new rocket. So a little bit bigger, a lot more payload capacity. 100 times the payload volume, at least 10 times the payload capacity. Here is a video, because rocket engines are cool to watch. Wait for it. Would you turn down the brightness? Anyway, they're cool. This is actually kind of cool. So this is what's happening literally right down the street from you guys. We have 2 indoor rocket engine test cells where we did thousands of tests. This is actually being, this test is occurring at our Castle test site, which is about an hour and a half from here because this engine would disturb the neighbors, especially if it didn't work. But, so this is using a tap-off cycle. Based on Ukrainian IP, we take the gases from the combustion chamber, we duct them into the turbine, And we have a single turbine that turns the fuel pump and the LOX pump. So basically, once this engine is running, it stays running because the combustion gases are what's powering the turbine, and it's a very simple, inexpensive engine to build versus other engines that effectively have multiple rocket engines that power the turbines. More valves, a lot more complexity. So we've really tried to figure out what is the simplest engine on the simplest rocket that you can mass produce. There's a lot of cool software stuff happening, but I'm going to run out of time. And this is a cool video. This is like oh, you didn't. This is the dark music. This is the Trump music. So with that, the reason why I'm here is because you should all come work for Astra. We're literally like 10 minutes from here. We have an incredible team. It's a startup again. And one of the things that I really enjoyed working on with Al is just ripping out all of the overhead that we took on as a company, as a public company, all the financial systems and compliance stuff, and just getting it down to this like really beautiful core. And so we're focused on how do we make engineers productive? How do we increase the velocity of the team? How do we increase the rate of learning on these teams? And so it's great to see all the different teams working on avionics, working on the stages, working on the engines. And we had about 25 interns this last summer. So if you're enrolled here and you want to like come do some part-time stuff, just go to this website. There's an application for a new graduate or a graduate position, just apply to that, and we'd love to have you. And it's one of the most fun. It's more fun than SpaceX because we're not on the border of Mexico where they'll chop your head off if you accidentally took a left turn, and you don't have to live in a trailer, and we don't make you work 6.5 days a week, 12 hours a day. It's appreciated if you do, but it is not required. So with that, I will wrap. Thank you all.
We would like to thank Chris Kemp for being our keynote speech, and we are going to open the floor for a quick Q&A. So if you guys have any questions, please raise your hand.
I love questions.
Yeah.
Yes, go ahead.
Hi, Chris. Thank you so much for that presentation. My name is Rama Fulo. I'm the founder and CEO of a company called Satellite, S-A-T-L-O-I-T. You spoke about software, and you said that there wasn't enough time to go into that. Like, I'd love to hear a little bit more about what the software angle is from the new Astra.
So yeah, very early on, we realized that data was important, and so we have a platform that I'm super excited to leverage, where whenever we do a test, we can actually take every sensor that's recorded every bit of data from any test in the entire history of the company. We have all that data. We don't use LabVIEW because that's like a toy. We take the data from the data acquisition devices, which sometimes are made by National Instruments but don't have to be, and it gets queued up onto a controller running a platform that we've built. It gets streamed up into AWS GovCloud. And then there's a massive data lake. So I can take all the data from, for example, all these launches, and I can take every sensor from every vehicle, and I can overlay them, and I can see patterns. This was actually super cool 5 years ago, but what's even cooler now is that you can use AI to tag the data, and you can find patterns and anomalies. And so we're in the process of building a GPU cluster right now. Most everything we've done has been published in a wiki. If it's knowledge and if it's an action, it's in Jira. So this Confluence Jira suite of tools from Atlassian literally contains the sum knowledge of every employee that's ever worked at Astra. And so we're going to train a model on all this information to effectively create Jarvis. So like imagine if every requirement, if every document from every supplier, everything that we've ever learned, every employee that's ever worked at Astra, were available to every employee that does work at Astra. And then you can ask it questions, and you can have it effectively cross-correlate these things on a model. So I think that's the short answer. Yep.
Next question up here in front.
Hi. You mentioned earlier that you're working with Anduril. Anduril is a defense company. They're kind of like a tech company. So I think of them as like the Silicon Valley of like defense. In terms of like loading Astra's rockets with Anduril drones and having them fly anywhere around, you're saying that it's a huge possibility that this is the new deterrent for World War III, and having that deployability and having that action. So in terms of like deployability and reliability, where does Astra stand on that?
Well, I think the Defense Department understands how important this capability is. So they've been embedded at Astra throughout the development of Rocket 4 to certify this as what's called a Category 2 capable vehicle. And so there's an enormous amount of, there was a real shift. Rocket 3 was the kind of cowboy rocket. Rocket 4 is the, okay, we know we can do this, let's do it right. And right is, it's not the $20 billion 20-year journey, but it's also not the, let's just throw it together and see if it works and not document it and not have. So there was a huge effort while we've been quiet to do a fairly comprehensive suite of failure mode effects analysis, systems engineering, test coverage analysis. So what's been happening at Astra is every single weld has been pulled 100 times so that we know exactly what the manufacturing process is for everything that goes in the vehicle. Because that'll pay dividends when you can knock these things out on a production line because you can automate the stuff. So we literally deployed hundreds of millions of dollars in a factory and hundreds of millions of dollars in an effort over many years to do the systems engineering and the work to make Rocket 4 something that can be mass produced at scale. The big idea was if you're going to launch a rocket every day, 1%, 99% reliability, like space shuttle reliability, not good enough, right? Because if you lose a rocket 2 or 3 times a year, are you going to really be able to fly every day? So the big idea was actually you can't get to scale without reliability.
Next question over there.
Hi, Chris. Right over here in the fourth row.
There you are.
Yeah. My name is Abhi Kumar. I teach the New Space Economy course here at UC Berkeley. In a previous life, I was also leading the partnership between Planet and Astra for a few months when I was at Planet. Two-part question. Question number one, and this might be 5 years before I should be asking this, but since I have you in the room, if and when you choose to go public again, what would you do differently this time? That's the question number one.
Yep.
And question number two, what you just described about Rocket Force, capability being deployed in different geographically disparate locations, sounds like almost like a tactically responsive launch capabilities, right? What bottlenecks or what roadblocks do you see, especially from a geopolitical standpoint, for that vision to actualize?
I want to take the second question first because it's just more fun. I think with this administration, it's just a question of can we send the right 24-karat gold-plated trophy situations to the right people? Because I think this administration really wants to deregulate everything, right? I think this administration might be the administration that makes America less protectionist in space, right? That abolishes aspects of ITAR, CFIUS, that are impediments to seeing American space technology proliferate globally. And so, say what you will of the rest of the policy stuff, but that is not a bad thing, because otherwise we're just going to see China and India just dominate global space, and that's probably not good for America. So that's the second answer. The first answer is, I think being a private company is great. Having all of my time focused on the business is great. As a public CEO, you have to focus a lot of energy on what's happening this quarter and what the analysts think of you and a lot of compliance stuff. You've got a board that's entirely independent from you that you're having to manage. Being actually running a business is a different thing, running a public business. If you have to be public, the one observation I would have, the reason why American manufacturing is just, screwed is because American public companies don't manufacture anything. They integrate. If you look at a Boeing or a Lockheed or a Northrop Grumman, they don't have machine shops there, right? They're buying parts from a bunch of private mom and pop companies that have no ability to scale. And so that was never our playbook. Our playbook was, you go to Astra and there are 20-foot bars of aluminum on shelves and racks, and there's a saw house, and we saw them into pieces, and we bring them in, and we have CNC machines, and we machine the things. That's important for development, because if you're trying to go fast, you don't want to wait for a part. If you go to any machine shop and you say, hey, I need this part, I need one of them, good luck. Okay? So if they work for you, and you say, I need this, our entire machine shop is working all weekend, this weekend. Why? Because I asked them to. Right? You can't do that if you don't control the company, right? Or you pay a lot for it, and then the costs go up. So, if the real problem is that if you're a public company and you have PricewaterhouseCoopers or whatever come in to audit you, and they start asking questions like, where's the oil that goes in the saw blade accounted for? That's annoying, but it's also expensive. And it means that you have a large finance organization and you have a large, you're paying $5 to $6 million a year for PwC to dig through all this stuff. So running a manufacturing organization with all of the detail and complexity of cost accounting and the accounting that goes on of all of these things, is expensive. And so what I would say is it's not impossible, but it's a huge hit to margin. And so I would say we need $1 billion of revenue at 30 to 40% margin before I'd even consider it, right? Because otherwise it's just too much of a tax on margin. It's like a rocket. I like to equate companies to rockets. If a rocket has too much mass, it just doesn't reach orbit, or you have no payload. So I would say a company is the same thing. Like if your company does not have enough thrust, like enough revenue, enough growth, then it will literally never reach critical mass, and it will not be able to stay a public company. It will not reach orbit. It will never get there. And that's really fundamentally what a lot of companies, that's the mistake a lot of companies made. They underappreciated the cost and the overhead and the friction associated with being public, and unless you print money, like a lot of tech companies that are just very high margin software businesses can grow that quickly, because you can grow revenue that quickly and margin that quickly. But a manufacturing business where you're having to scale CapEx and hardware, it's extremely hard to be, it's hard to be a small public manufacturing business.
Thank you.
I would be a large public manufacturing business. That's right. Cool.
Last question? If you could come up.
Hello. I had a quick question, sort of a follow-up about your new approach in terms of launching from different geographical areas. How is Astra kind of going to find the balance between giving your potential clients, who may be nation states, giving them as much flexibility in terms of launching how they want to, and kind of also finding the balance between, hey, you're not giving up too much and they're not able to back engineer it. So how does that balance between knowledge transfer and export restrictions kind of, what's your ideal view on that?
I mean, even a spaceport is considered ITAR, right? Because it's where the QD interfaces with the rocket, that's IP. So if you really want to respect ITAR, just put the entire thing in shipping containers, show up on a dirt pad, and take it with you when you're done. There isn't another rocket system that can be deployed that way. It's how the Patriot missiles are protected. Like literally, you can just have someone that works for the DoD with the thing and don't have them leave. And put cameras with AI on it, and just make sure that your IP is protected. That's the answer. No other system can be deployed this way, which is why the launches are being done in the Five Eyes, which is our most strategic intelligence partners first. But beyond that, I think this is the ticket, to see American space technology really proliferate around the world. Good. With that. Such a pleasure. Thank you. Thank you. Oh, love. Thank you. Oh, wow, this is great. Amazing. Thank you all so much. Such an honor. Appreciate it. Yeah, I'll give it to you. I'll take it right off. Thank you. Thank you.
Right now we are going to go into a 15-minute break, so. Please be back in 15 minutes. Our panel will start soon after. Thank you. Where's Jacob?
They're doing a quick picture. That's all. He gave the mic is right here. His lab is. You have my phone. It was on the.
It was on stand. I just grabbed it.
Did you get? Did you get Jake? Can you get a picture of Jacob and because he wasn't able to get on?
Yeah.
Well, yeah, I know. When they're moving out. Hi. Yes.
Did you want me to sit in the front and you're doing an intro? Or?
Yeah, someone will intro you.
Okay.
It will be Deer, the kind of taller Indian guy. I don't know if you saw him.
Yeah.
He'll intro you. You'll be sitting here, and then we already have a layout for where the speakers are sitting.
Okay.
So it'll correlate with how it is.
Awesome. Okay, sounds good.
Do you want?
Yeah, I'm just going to walk Chris up to his car.
last word.
Hello? Hi, everyone. Thank you so much for joining us again. We're very lucky today to be joined by an amazing panel. Dr. Abhishek Tripathi will be moderating the panel. On the panel, we have Dr. Eugene Tu, who is the Dr. Tu is the Center Director for the NASA Ames Research Center. We also have Al Tadros, who is the CTO of Redwire Space. We're also joined by Dr. Elkin Stanton, who is the Director of the Space Sciences Lab. And lastly, we're joined by Alex Drossler, who is the Director of Mission Design at Momentous. We're also honored, Dr. Abhishek Tripathi will be moderating the panel today. He is the Director of Mission Operations at the Space Sciences Lab as well. Over to Abhi.
All right, this is like my second year moderating this panel now, so I'm really excited to be back. I think one of the most interesting things about having a panel up here is learning a little bit about their background, how they got to where they are now. So I was wondering if I could start at the end with Dr. Tu. Give us a quick bio of your journey to here.
Okay, thank you. Well, it's really an honor to be here with all the panelists and with yourself. And it's to me, being here is coming back home. I graduated from here in 1988 with mechanical engineering, and I grew up in the Bay Area, and my career journey started while I was here. I interned at NASA Ames, and I've stayed there ever since, so 40 years now. It's an incredible opportunity, and I just came back from talking to the aerospace engineering class, which there was not a dedicated aerospace engineering program here. So after I graduated, I did go on to grad school. I went to that school down south that nobody talks about up here, and that's where I got my PhD. But my journey has been starting out in research in engineering, aerospace engineering in particular, moving on to program project management, and I've been leading NASA Ames Research Center for the past 10 years now. But it's really, coming back here is really an incredible opportunity, so thank you.
Great.
So again, I'm Al Tadros. I'm CTO at Redwire. I've been with Redwire for 5 years. My career in aerospace engineering started actually in high school. Space Shuttle just launched in 1980 when I was a freshman. A lot of excitement, and NASA wanted to get students involved in the shuttle program. I happened to align a science fair project with the shuttle, which I can talk about more later if you're interested. But it inspired me to enter the space industry. I was lucky enough to get to MIT, which had an actual aeroastro program. So there just weren't that many around the country at that time. And even then, as I was shared, there were only 100 students in the aeroastro department at the time. So there were small departments, but that's what I graduated from and drove my Honda Civic across the country to take a job in Palo Alto at a company called Ford Aerospace at the time. And I was convinced that it was the right time to come out here because the '89 earthquake just happened, and I figured for the next 100 years I was safe. So that's my pseudoscience on earthquakes. You can share that. So I've enjoyed the opportunity to work on a lot of different spacecraft, commercial satellites, geostationary satellites, and probably the biggest commercial space industry for many decades was the geocomsat industry. But I worked on a number of other missions, NASA missions and DoD missions. Got a chance to work with Lindy on Psyche. So it's a breadth of space robotics, satellites, and other things that I had the opportunity to work on. And when I thought I was in the happiest place, I had the opportunity to join Redwire, which was just forming, and we'll talk more about it, but basically growing by acquiring and integrating space companies into a mid-size, prime capable space industry. So it's an exciting opportunity for me to do that in the last 5 years, and it's been exciting. And as I've shared, this is the most exciting time ever in the space industry right now, and we can talk more about why.
Hi, everybody. I'm new to Berkeley, but I've had a sort of long, winding path. I also started out at MIT about the same time as you, but in Earth and planetary science. So I'm a geology geophysicist. And after that, I went and worked in the private sector as a management consultant. I ran my own business, writing business plans for high-tech companies looking for venture funding for a while. Unbelievably useful experience. I also raised sheep and trained border collies. Also very useful. And then I went back. I went back to school to get my PhD. Again, back to MIT. 10 years after the rest of the cohort, when I was 31, and a single mother. And my son started kindergarten the same week I started my PhD. So I had a bit of unusual pathway, and went into leadership in academia. I've been at Brown University, the Carnegie Institution for Science in Washington, D.C., and I was on the faculty at MIT. And I'm really obsessed with how you get teams of people to work such that the project succeeds and every individual person also succeeds on their own behalf. And that's really what I became passionate about. And back in 2011, started the process of proposing to NASA a major mission. And that's what Al and I got to work on together. We picked what was then Space Systems Loral, and it's now Maxar as our prime. And in 2017, won, after 3 years of competition, the Psyche mission to what we believe is a metal asteroid, the first metal object that humans will ever visit. And we launched in 2023. Oh, and I just have to gratuitously add that in 2017, when we were selected, I became the second woman to ever compete and win a major NASA mission. And that is a hell of a process, I will tell you. So, I mean, that's nice, I appreciate it, but I just want to add that mainly because the competition process for giant proposals is an art unto itself, and I'm here to talk to anybody who wants to do that. I spent 10 years at Arizona State University as a director and a vice president working on space-related initiatives, and was so excited to come here starting July 1st as the new director of the Space Sciences Lab up on the Hill. If you haven't been, you need to come visit, and also faculty in Earth and Planetary Science.
Hey, thanks for inviting me. Nice to be on the panel with you all, and definitely want to take you up on that visit of the SSL. It sounds so cool. I have a very wide-ranging background. I started actually from an international affairs degree at George Washington University in D.C. Had a couple startups, one sunglass company and a little bit of a food network in the early 2000s. Yeah, I had a lot of swag. I'm starting to run low on my sunglass swag now. And then worked also for about 15 years in the art industry doing art logistics, and ended up running a small company, or I guess medium-sized company here, doing all the background work for museums, art galleries, and private collectors. So actually did several installations at the Berkeley Art Museum and Film Archive here on campus, before when they were at the old building, and then some when they were at the new building here as well. Ultimately, when I was growing up, like, I used to go actually see some of the space shuttle launches in Florida because my grandparents lived nearby, and I would always make my parents like drive me out in the middle of the night to go check them out, and it was like an amazing experience. So eventually I realized, oh man, why am I not doing anything in space? And I really want to do some like big projects, infrastructure projects in space. So went back to City College in San Francisco, took advantage of, like, you know, the education system that they have there, and they have an amazing pipeline for grads getting into good schools, especially like, you know, UC Berkeley. Ultimately, I ended up going to San Jose State because they had like a kind of a system where you could get directly into a master's program for aerospace engineering there. So took advantage of that. While I was there, ended up tutoring some undergrad students. And when I graduated with my master's of aerospace engineering from San Jose State, I was looking around for a while on like what type of companies seemed really interesting to work for, what type of roles there were out there for me, wanting to kind of do big projects, designing missions in space and things like that. Ended up encountering Momentous, which really has like this vision of being the infrastructure backbone for space and helping the entire industry kind of grow up, especially in the new space side. And it turns out one of the fellows who I had tutored while I was a master's student was working there. So I saw a couple interesting job openings, one for a mission design engineer. I hit up Stefan, like my 2T, and I'm like, hey, what do you know about Momentous? How do you like working there? Do you know anything about this role? And he's like, oh yeah, like actually let me look into it. And it turns out that his manager was the hiring manager for, at the time was a mission design systems engineer role that I ended up getting hired for, and then have been there for about 5 years at Momentous since. Now I'm the director of mission design, really kind of doing a lot of the work across our whole team and across industry to bring in new customers, figure out what types of missions we can do for them, supporting, you know, both industry as well as academic and U.S. government and other international partners, and seeing how we can support people getting into space and fulfilling their dreams in space. So yeah, happy to talk more about circuitous routes to space anytime.
So one of the things I hope the audience has noticed is you have a really good mix here of government, commercial, and academia, right? My own background, just to chime in really quickly before going on to another question I want to pose, is I spent 10 years working for the government at NASA. I spent 10 years working in commercial with SpaceX, and now I've spent the last 5 years here. And I really see how all three of these verticals work really closely together. So the next question I want to pose, starting again with Dr. Tu, is tell us a little bit about your organization and tell us what you see as the strengths of your particular segment, as well as if there's any areas of very active collaboration you see. And I'm going to ask the same question so we can get a feel for the commercial side and the academia side as well.
Okay, thank you. Yeah, no, so NASA Ames has been a long-standing institution here in the Bay Area. We are turning 86 this year, so we started in 1939, a good 20 years before even NASA started. And so we're one of the research centers for the agency, and that means we work in almost all areas that NASA works in, whether it be aviation aeronautics, whether it be space exploration, whether it be science, and whether it be technology. So one of the key things, now I personally feel it's the coolest center in the agency, but I'm biased that way. But one of the reasons is because of the type of missions we run and we operate. So we're responsible, for example, on the aviation side on aerospace operations research, looking at advanced air mobility, and that's an area actually we're partnering very strongly with Berkeley now on. On the space exploration side, we are the primary center for entry systems. And so almost every spacecraft in the US that has gone through a planetary atmosphere, either returning to Earth or another atmosphere, has gone through our facilities or is actually using our materials to protect the spacecraft. And then the primary mission focus now for NASA and the priority is around exploration and moon to Mars. So returning humans to the moon and moving on to Mars and getting humans to Mars. And so one of the key questions around that is the space biosciences part of that, the biological sciences, the human research that needs to be done, because we are only experienced, quite frankly, for long durations, and long durations meaning only up to a year now on the International Space Station in low Earth orbit, and for a few days on the moon from back in the Apollo program. So really extending human presence for long duration to the moon, and also for a multi-year mission to Mars, there are a lot of biosciences and human research questions that need to be answered and addressed. The final point I'll make is that, and I think you touched upon that right at the beginning of your question, today is a very, very exciting time, I think, to be in aerospace and to be in space. One of the reasons is because of this, I'll say, this new space economy that's coming up. And if you think about it, it's analogous to what happened with aviation over the last 100 years, where aviation started out primarily as a government-funded, government-researched activity. Now it's largely a private sector, marketplace-driven activity that affects everybody's everyday life in one way or another. We hope and we are looking for space to become that as well, and we're starting to see that because we have companies now, and that's one of NASA and the government's mission, is to try to enable these companies to be successful, buy down risk for them, so that they're able to create a space economy and grow the investments in space and space exploration to the point where it really does affect everyone's everyday life in a very positive way, right? So that's what we're looking for, and it's the partnerships that enable us to do that between government, industry, and academia, and that's really part of what's really exciting about what's happening. Last plug for what's happening down in our campus is UC Berkeley is planning to build the Berkeley Space Center there on 36 acres of our property. They're going to be building up to 2 million square feet of R&D space, offices, conference space, educational space, and really try to merge even more tightly the collaboration between university, our joint research, our joint industry partners, and government laboratories.
Great. So Redwire was envisioned and grew over the last 5 years. So the vision was to acquire, integrate, and scale proven technologies from basically small space companies. So we've successfully gone through 12 acquisitions. And for the business majors in the room, you probably have a stack of books that say how M&A does not work most of the time. So just like with any other skill, you learn and you improve and you get better at it. And after 12 in 5 years, we have a process that actually works very smoothly. So that is one of the skills that we have developed in the space industry, which isn't very common. The value of scaling in the space industry is that things cost a lot when you build them one time, and things eventually get lower cost and more, available if you have a manufacturing and a business operations that can actually produce the capability in volume. So that was the vision and the intention. Through that, we acquired a company called, for example, Deployable Space Systems. This is a company in Goleta, down in Santa Barbara, California, that had developed the rollout solar array. Most of you have probably seen the new solar arrays deployed on the space station. Amazing technology, simplifies the heck out of deployable structures by using a composite split tube boom and then a flexible backing for solar cells. 25 kilowatt to 50 kilowatt type of solar arrays rolled up and stowed in the trunk of a Dragon capsule. Those kind of technologies. They had developed a lot of it, and not only for space station, but for some other missions. And we have now been able to scale it to use it on everything from planetary exploration to commercial geosatellites and more. They are also now developing that capability, and to the question about kind of unique technologies and differentiators, to be able to deploy a vertical version of that on the lunar surface. So think about going from microgravity or zero gravity in space deployments to a 1/6 Earth gravity deployment in a dust environment. So the transition into an application where we might have hundreds of kilowatts in order to power a base station or a science kind of expeditionary mission on the lunar surface. Those are the kind of applications that power system is going to be applied for. Another acquisition we made was doing basically rocket bodies for a solid rocket motor company. So if you combine solid rocket motors with a rocket body, all of a sudden you have a small rocket. And we're doing that with a company called Crossbow. And these are suborbital rockets, but they have tremendous capability, multi-stage, and now there's applications for that same capability from space for space-based interceptors. And there's an example of a transition of a capability that goes from basically suborbital technology development and science missions to defense application. And then one final mission that we grew into with a few different technologies is VLEO, or Very Low Earth Orbit. This is where you're actually flying in the outer atmosphere, and both have to survive it, but the question is, can you make use of it in a air-breathing sense? And if anybody's a physicist here and wonders what they can do in space, there's plenty of work to do in the space industry. So there's a lot that we grew as step functions, and like I said at the beginning, this is the most exciting time in the space industry because there's a lot going on, everything from aircraft and suborbital to the lunar surface that you can enjoy.
Wendy?
I think fundamentally everything we're talking about here today is exploration. Even if it's purely for commercial, Earth-facing, low Earth orbit, the thing is it's space, and that gets us excited. We're doing something that humanity's never done before. We're going to space because we can't resist. And we're not just doing Earth orbit, we're going into Earth and Moon orbit, we're going into deep space, and we've got instruments out there looking much, much further, trying to understand, give us this perspective on who are we as humans. And so that's where the university centers really come in strongly. Space Sciences Laboratory was founded in 1959, And right now we're about 260 people. Doing the entire menu of space exploration, from designing new kinds of sensors and instruments, not just for science, but for things like radiation measurement, space weather, storms, human safety, particle detectors, and then actually building, designing, proposing, and launching and flying whole space missions, soup to nuts. And I don't know if you really took in that our moderator's job title up here, Director of Mission Operations, I mean, that's not a euphemism. We are literally flying missions in space right now, controlled from the top of the hill here at Berkeley. And there's only two universities in the United States that can do that entire thing from the beginning to the end. We've got a 15-meter dish. We link into the Deep Space Network. And I think most importantly of all, we partner in so many ways. We partner obviously with the government, and we do an awful lot of work for NASA, and we partner with private sector. But training and workforce is so critical. We have so many students who come up and work with us, PhD students, undergraduate students, summer students from other organizations, and that is the most beautiful way to step out into the aerospace industry, having literally handled and managed flight hardware yourself. And so this is just a beautiful part of the Berkeley ecosystem that I'm really proud of, and I want everyone to know more about it.
Thank you. Alex?
Hey, yeah, so, I mean, what Momentous does is we really are trying to be the in-space backbone for services, missions, and especially our customers. What we do primarily are in-space delivery services. We also have hosted payload services and also use our spacecraft bus to provide full spacecraft to our partners. Over the past 5 years that I've been there, we've actually launched 3 spacecraft. What we do are Vigoride spacecraft. They're an Espa Grande-sized vehicle, so about 250 kilograms without any other payloads on board, but then we launch up to about 500, 600 kilograms total. What we're doing is all about partnerships, and it's really exciting because, like, for example, our mission that's upcoming, Vigoride 7, we have payloads from NASA, from DARPA, from industry partners, as well as our own in-house developments for doing things like rendezvous and proximity operations. So, you know, the big innovations that we're doing are really driven both by our customers, by what their intentions are and helping them get their aspirations to orbit more quickly, but also seeing where we can develop our products that are more tailored to how to do things on orbit for, you know, interesting projects that are upcoming in the future. So, yeah, I mean, that's kind of one of the things that I love being in new spaces, just like the speed with which we do missions. I mean, it's like I've been here only 5 years and already done 3, planning a 4th that's launching in February and looking at 2 more in 2026 and 2027. So, yeah.
Great. So I've now moderated enough panels to know that whatever questions I come up with will not be nearly as good as questions from the audience. So I'm going to ask only one more quick question, and I'll let you raise your hand after I ask the question, whoever thinks of an answer first, and then we'll get from the rest. What is the most important piece of advice you can give or prediction you can make to help the students that are in this room here today be part of the next generation of successful doers in the space industry?
I think that the most important thing you can do is come to places like this, make personal connections, and do internships or get involved with research, like do the real thing while you're doing your class. That is the way in. Do you guys disagree? What do you think?
Yeah.
It's a small industry. The people you're going to classes with, you're going to interact with throughout your career.
Yeah, the only thing I would add is, especially these days, I think breadth is as important as depth. And so for students nowadays, you need to be exposed to areas beyond maybe your major and your focus. Because space is going to involve all disciplines, whether they be engineering, whether they be business, whether they be law. right? And finance and art and communication and all of it. So to the extent that you can broaden your horizons and look beyond maybe only your area of focus and study, that will help you when you go into space industry, because it's going to be an all-of, I think, endeavor.
Yeah, I also think that, don't be bashful about going for something that you're passionate about. If you see a role that it feels like, oh, maybe this isn't exactly what I, fits my experience level, but this is something that I really want to do, just go after it anyway. And if you can show that you're passionate about that and that's where you are going to excel, I think that's, it comes through.
Yes, that's the guy who moved from art and art installations to orbit. I mean, that you're proof right here.
Yeah, I mean, you go for it, you can do it. I mean,
So I'll add mine, and then I'll take questions. One thing I find in this generation, a lot of people are very motivated. They want to be entrepreneurs. They want to be founders, right? But you can't go to school and learn how to be an entrepreneur or a founder. You have to wake up every morning with a problem or a burning desire to fix something. That's the only sustainable path to being an entrepreneur or a founder. So remember that. Study and learn things in school so that you can go work on that problem that you're burning to go work on. So, all right, I'd like to take questions for our panel. Yeah, right here in the front.
Oh yeah, it's working now. I teach my name is Abhi Kumar. I teach the New Space Economy here at Berkeley. One of the two case studies that we did within the classroom was on Redwire. And we analyzed Redwire's M&A heavy strategy. So two-part question. Number one, how long do you expect your company to be M&A heavy in terms of its strategy? Do you foresee any kind of regulatory roadblocks in the future? And number two, as a publicly traded company, how do you balance like quarter by quarter performance issues and concerns with, as a CTO, I'm sure you have like a long-term technology roadmap. How do you balance between the needs of that of a public company, public listed company, as well as a technology heavy company?
Okay, very good questions and very substantive. First of all, I don't foresee any slowing down of M&A, and this isn't news. Our CEO and CFO do earnings calls every 3 months, and they specifically talk about the fact that we're continuing to grow through M&A. The last company we acquired actually doubled our size, roughly. And it was not a pure space company. It was a defense contractor building some amazing UAVs or UAS platforms. Huge technology-driven capability. As everybody has heard recently, a huge discriminator in the defense industry, that kind of capability. And meshes very, very well in an era where autonomy and OODA loops, very fast OODA loops are critical between space, air, and ground. So that was the most recent acquisition. So to just sharpen that point, we might have a great vision, but as we go along, it isn't just a static market and environment. There is an evolving, international and national kind of ecosystem that we're responding to as far as markets and business plans and so forth. So I don't foresee any regulatory challenges. We're still relatively small. We're about 1,200, 1,300 people, and publicly traded, so financials are out there every quarter and so forth. And then the second question was, you asked the second part of your question?
I was thinking about your first answer. That's fine. We can just leave it. I want others speak.
I'd like to see the case study and what the students thought of each acquisition.
We had very varying opinions.
Right here in the middle.
I had a question for Dr. Elkins-Tanton. Can you tell us more about the roles that undergraduates play in the current active missions that SSL is running, aside from the stuff I've already seen, like with germanium detectors?
I can give you one example. We hired somebody from the computer science department, okay, and we wanted to make front-end GUIs, graphical user interfaces, for how we interact with and control our spacecraft. And a lot of times when you have a student coming up, the folks are like, yeah, but it'll take a while to train them, and do we have the time? And I think I made it a point we have to hire students. That's an integral part of how we should do operations. And this student just knocked it out of the park. I've had people from Northrop Grumman, Lockheed, Rocket Lab come into our Mission Operations Center and say, holy crap, how many people do you have to make all these GUIs? And I told them, oh yeah, a student did it who we've now since hired. And they're just, what? And so I think it's important, and I saw the same thing multiple times at SpaceX, where a student that was a sophomore or a junior was presenting their work and their innovation directly to Elon. Okay, so I think undergrads can do a lot, especially super motivated undergrads, and the SSL absolutely wants to take advantage of that, to be honest with you. We want you up there, we want you doing great things.
If I could just add briefly to that we do, and so being new, I don't know all the stories yet, but I know we've had undergraduates across the engineering experience, but also in the science experience, analyzing real data, coming to new science conclusions, writing peer-reviewed papers. And I would just add on Psyche Mission, just this summer, we had a summer intern who was analyzing the likelihood of spotting tiny moons around the Psyche asteroid as our spacecraft approaches. And she was, at the end of the summer, presenting her work to the whole 300-person team. And so it's everything.
I have to make a plug here for it, just also because NASA Ames is also very much interested in students, particularly undergrads, and having them intern. Working with Professor Papadopoulos, we've had about a third of the aerospace engineering class each year intern with us. So it's really an incredible opportunity to both ways, right? Students learn, but we also get so much benefit, as you pointed out.
Let's see, over there on the right.
Thank you so much for your time. This has been really interesting. There have been some discussions about breadth and also space, not just on the engineering side, but on the business side. I'm very curious about your views on pathways into business strategy ops type roles in the space industry.
Well, I mean, there's a variety of space industries, and quite frankly, there's companies that are very conservative and very methodical. They look for a government contract, and they work that perhaps for years. And then there's innovators that push the limits, and probably to their detriment in the business end of things, because just business operations is hard enough, let alone technology development in the midst of business. So the entry to that. I work with a private, we are private equity owned as well as publicly owned, and we work with a number of, finance, legal, policy. So there's a number of entries from those directions. There are law firms, Hogan Lovells comes to mind, that has specialty space entries. There's a number of finance now, and more private finance in the space industry that you can enter through. Quite frankly, that is the harder part of getting a scalable, sustainable space industry. The question earlier was about how do I think about technologies. Well, there's a lot of technologies that we can go after. There's a lot of technologies just to get some basic stuff working reliably. You don't have to think that hard to, in the space industry. So being able to work with technologists or with manufacturing is another entryway to the business side. An operations team that can forecast, hit their EACs, hit their margins, is golden. In fact, I say frequently, and I'll say again, I think I'm on camera, if you want to be a disruptor in the space industry, hit your numbers. It is. It's not that often that you see one that does that.
Okay, I think we've hit our time limit here. Some of our panelists might be here later today if anybody wants to catch them in the hall. Appreciate all the great questions we got from the audience. And thank you again to all of our panelists for spending the time talking about their
One more thank you for all of our panelists for the incredible insights they provided. You just get one more round of applause for all of them. We here at New Space wanted to give a small token of our appreciation for all of our members. For all the other people in the audience, next up we have the CEO of Muon Space. We have Johnny Dyers. Yeah. Once more, can we get a special welcome for our next panelist, Johnny Dyer, the CEO of Muon Space. Please give him a warm welcome.
Looks like I really scared everybody away. I don't know. Are we able to get the slides up? Well, while they're doing that, let me introduce myself real quickly. So I'm Johnny. I long ago went to a school that I won't name for fear of my own safety, but it's another Bay Area school. I was a mechanical engineer there. I've met a lot of mechanical engineers today, so I'm really excited to see that tradition lives on. And I've done a lot of stuff in space in my career. Early on, when I was in undergrad, I actually interned at SpaceX. In the very early days of SpaceX, 2003 and 4, I was one of 4 people in Texas at that time in SpaceX, so that was literally the Wild West. I also got some really unique opportunities to work at other very important startups along the way in what has become kind of the new space revolution. So I was early at a company called Skybox Imaging, which many of the younger folks in the crowd may not even remember, but this was the first venture-backed sort of new space satellite company founded in 2009. We went on had a really fantastic journey there where we built and launched 21 high-resolution imaging satellites, ended up getting acquired by Google, and then later sold again by Google. And then did a number of other things in my career, including some time in autonomous vehicles, as well as advising on a number of things in space like MethaneSat, which is a global methane emissions monitoring system that launched a couple of years ago. And so I've gotten to see and do a lot of different things, much of which has now culminated in what we're doing at Muon Space. So I'm really excited to kind of tell you all a little bit more about that. I'm actually going to see if I can grab one of these microphones so I'm not leaning over. Test, test. Does that work? Okay. That's better. So I think Muon Space is about 4.5 years old. We were founded in 2021. We're about 175 people. We're right in the Bay Area, down in Mountain View on the peninsula, so another local company. We're growing very fast, venture-backed. We've raised 3 rounds so far. We have launched 4 satellites to space, 4 working satellites to space to date. And there's a ton of exciting stuff coming up on the roadmap. So I have some slides I'm going to go through just to kind of frame a little bit first about how I see the overall landscape in space right now, and then how I kind of see Muon fitting into that. And then I have a couple of examples of some of the work that we're doing that I think will be exciting for people. And I'm going to try and leave enough time for questions. I actually don't know exactly how much time I have because we're a little bit late, so somebody will have to keep me honest, and I'll try and get through the slides as quick as possible. I think as can be seen from events like this, space is very hot right now. We all got to see the pretty awesome Starship launch a week or so ago, and there's just a ton going on. It's a very hot topic across all elements of society. Investors are interested. There's a lot of money flowing into it. And so, it's this really compelling, exciting time. Even in my career, I've seen that kind of excitement level or interest level rise and wane, and I think we really are on an upslope right now. And it's been changing really fast. I think that's a really important consideration. I look back to the time we spent at Skybox, which was a little bit more than a decade ago, and we were flying to Southeast Russia to launch satellites off converted Russian ICBMs. And the cost to do that was something like 10 times the cost it is for us to launch satellites with SpaceX today. So you think about how much has changed in what's a little bit more than a decade, even from the basic perspective of access to space, and it really dramatically transforms how you think about what is possible to do in space. And I made this plot a couple of years ago. I really like this plot. It's actually now out of date, and it's probably, the numbers are probably even higher now. But this is a plot of the number of satellites in low Earth orbit going back, about 20 years, not quite 20 years. And there's a couple of things that you see on here that I think are really interesting. First of all, if you go back further, the number's flat. It was actually flat kind of into the early 2010s, and then it started rising on this kind of 5-year doubling slope right around the time that we founded Skybox, and that was kind of what I would consider sort of the new wave, or the first wave of this new space thing. What's really interesting is there was an inflection point again around 2020, and you now see that the number of satellites in LEO is doubling about every 18 months, and doubling every 18 months is Moore's Law, and we've seen what Moore's Law has done to the computing industry, and so you can imagine what this type of dynamic can do in terms of a feedback loop for an industry and driving it forward. And I think we're just at the very earliest stages of that. I mean, obviously a lot of this is being driven by things like Starlink getting launched, but that same capability to put things in space at lower cost, faster, and higher volumes is going to affect everything we think about in terms of how we do stuff in space. And so, we have this ability now to do things faster, better, cheaper. The question is, to what end? It's wonderful to be putting a bunch of mass in space. It's wonderful to be watching rockets. I love rockets. They're really cool. But, like, what are we really trying to accomplish? And so I gave a talk, sorry for the reference here. Many of y'all are probably too young to know this reference. During the Clinton campaign in the 90s, Jim Carville came up with this phrase for the Clinton campaign, which was, "It's the economy, stupid," and it became a very well-known, iconic political mantra. So for us, we like to think about it's the mission, stupid, and it's really not about the rockets and the fire or even the hardware, but it's like, what are we using this capability to solve? What problems are we solving for real people in real ways on Earth? And I love this picture. This is Apple's SOS system, emergency SOS satellite system, and a bunch of Skybox alumni were actually the founding team at Apple that built this product. And the thing that's so compelling about it to me is that for any of us with an iPhone, if we're out in the woods and we need help, we'll pull up our iPhone and use the service without really even thinking about the fact that it has something to do with space or its satellites. And I think many people use it never knowing that. So it's having this very profound impact on a lot of people's lives in a way that's totally transparent, is very impactful, and is really fundamentally enabled by a lot of these things that have been happening in space for the last 10 years. And so what we're trying to build at Muon, we think about as sort of a mission foundry. It is, our model is not that we're going to own every mission. It's not that we're going to solve every problem. But we want to enable that for many different types of partners and customers across a wide variety of organizations, companies, institutions, and really try and do that on a common platform. One of the problems today still with space is that if you try and do something new in space, it's still a very hard process. You have to develop hardware, you have to develop software, you have to have operations, you have to have a ground network. In many cases, you're developing a cutting-edge electronics package to do the data communication or the remote sensing. And we're now at a place where there's so much lower barrier to entry in many ways, things like the cost of launch, the access, the amount of launch that's happening. What we need to do is we need to lower the rest of the barriers of entry so that we can solve many, many more problems in space. And so the way that we kind of approach that problem at Muon is by partnering with entities that have a very particular problem they need solving. that is addressable in some way with a constellation of satellites in space, and then working, kind of arm in arm with them from cradle to grave to develop a solution to that. But really by leveraging a bunch of common building blocks that we've developed in a platform that enable us to do it quickly, economically, and scalably. And so we like to say, we design, build, and operate satellites for customers addressing some of Earth's biggest problems. This is a cool picture of our third satellite that was launched, getting integrated about 6 months ago in our clean room in Mountain View. I'll talk more about this in a little bit, but this is the first of what we call our FireSat constellation. So what you're seeing here is a multispectral infrared payload getting lowered down onto the spacecraft bus. That's satellites now in space producing data, and I'll show some of that later. And so when we engage with a partner or a customer, we like to think about 3 relatively simple questions. This may be obvious, but many times with technology-focused companies, I think these questions don't get asked early and often enough. The first is, what is the problem that we're actually trying to solve? It's not what is the technology, what is the capability, it's anything else, but ultimately, what is the problem we're trying to solve? The second one is, who cares? And the third one is, given who cares and what the problem is, what are some things we could actually do to solve that problem for that person? And I have in the backdrop here, again, a picture of wildfire. Well, in California, we all see very frequently how big of a problem wildfires become. And one of the missions we're most excited about is FireSat. And again, I'm going to talk a little bit more about it in a second, but it really grew out of us working with a set of partners trying to deeply answer these questions. And the way that we go about that is we engage in something called formulation. This actually came out of, this was a concept that came out. It's an old concept in space, but it was really honed at JPL in something called the Innovation Foundry at JPL. And you can think about this as a very rapid feedback-rich iteration around a problem statement or a mission need that's done cross-disciplinary, in a very cross-disciplinary way. We have scientists involved, we have engineers involved, we have business people involved, and we have our customer involved. And we find that this process is often, A, not done well or not done at all many times when somebody's trying to deploy something new to space. And B, it's really critical to do this well early in the process to get a good outcome. If you really want a solution that is going to solve the ultimate problem, going through this process early and often is really important. And we've built up a bunch of technical tooling around this to make it a more modern, more scalable process. An example of that is our simulation environment. So this is a very high fidelity physics simulation that we've built for modeling everything from, you can think about power, thermal, attitude control, our communications network to satellites. In many cases, the way that an instrument or a payload is collecting photons and how all those things integrate together so that we can, in a digital space, long before we've cut metal or had to build anything, turn knobs and see how we get the most out of a system and how we try and get something that is optimized not only for a performance requirement, but also the time it's going to take to get into orbit, the number of satellites we can put in orbit, the cost that it's going to be to do that. And so this is a really powerful tool that we've built that enables this approach. This is some other cool videos just showing various ways that we use the tool. And some more. I'm going to keep going so I don't waste time on this. The second thing that I think we've really tried to focus a lot on is it's one thing to build custom bespoke missions. The primes have been doing this for years. NASA's been doing this for years. The problem is, how do you do this efficiently? How do you do it in a way that isn't, costing billions of dollars and taking a decade? And we really think the solution to this is a very modular, very flexible, and a very repurposable platform that spans the satellites that we're putting in space, the software running on them, and the network that we use to communicate with those satellites, so that when a customer comes to us with a problem, instead of doing a bunch of custom design and development on new hardware, new software, et cetera, we can often address that problem largely through some configuration and some tweaking at kind of the top level on top of the set of common building blocks that we have already developed and proven in space. You can think about this a little bit like, the analogy I like to use is like Lego Mindstorms. You can buy a Lego Mindstorms kit. I don't even know if it's still called Mindstorms. It used to be called Mindstorms, but it's a robotics kit. It comes with a bunch of parts, and you can build a robot or a dump truck or conveyor belt, or you know, I don't know what else, a bunch of different things with those same basic building blocks. And we see this as an analogy to the way that we need to very rapidly iterate, integrate, and deploy the right solutions to space to solve particular problems, but on a timeline and a cost that is not traditional in space. The satellites, just to give a little bit of sense for what we're building today, kind of come in two general flavors. We have about a 200 kilogram spacecraft we call the MUSAT, and this is the primary one that we've launched to date. So we've launched 3 of these so far. They are, about 200 kilograms, can produce about 200 watts. This is what, for instance, our fire instrument is flying on. We're also developing a much larger spacecraft we call the XL, which is about 500 kilograms. One of the things I think we see as a trend, aside from the other things I showed in terms of the number of satellites in orbit, the cost coming down, is obviously things are getting bigger, Starship being the canonical example. But as we get things like Starship coming online, and not only the launch cadence getting higher, but the amount of mass you can put in orbit, it really starts to change how you think about what the unit economics in space are. So traditionally we've been very focused on how do we pack as much into small spaces as possible. This was really a key insight in the early days of Skybox. We need to build small sats. We talked about small sats solving these problems. A lot of that was driven by the constraints of launch. As those launch constraints relax, it really changes how we think about building satellites. And we believe the future is actually going back to much bigger satellites, but doing it at sort of the costs and timelines that you might see traditionally for something like a CubeSat. And so our roadmap includes a lot of scaling into larger and more capable spacecraft, which then allows you to do things like collect more photons, or give a payload more power, or push more bits around a system, and that then gives a lot more capability. The other thing that I think is a little bit unique about us that I'm very excited about is, often with these missions, the spacecraft is necessary but not sufficient. The ground segment is necessary but not sufficient. Really, ultimately, what the moneymaker or the problem solver is the tip of the spear. It's the payload. It's what is moving the bits around. It is what is collecting the photons. And one of the other things we discovered early on with several of our missions is, as we went through the formulation process, developed a concept for what really needed to get built to solve the problem, is that the first roadblock you run into is that payload does not exist. And so we've also, out of necessity, taken on developing some in-house capabilities on the payload side, which then allow us to fully vertically own and deploy a lot of these very, very, very high performance systems. Things like the infrared camera I'm going to talk more about on FireSat, as well as a bunch of radio frequency payloads we're developing for a number of customers that span both remote sensing and communications. And so I've kind of alluded to it a bunch, and I wanted to just spend a few more minutes talking about this, because I think we see this as kind of a marquee example of the value of our approach, kind of this mission foundry, mission first approach, actually kind of being manifest in a problem that we can all relate to and are very excited about. So FireSat is a cross-organization partnership that we are one of the members of. It also includes a nonprofit called the Earth Fire Alliance, which is a 501c3, so a U.S. nonprofit, whose mission is basically to transform the way that we manage wildfire in the landscape by providing land managers, first responders, operators, sort of a sea change and situational awareness around where fires are, how they're burning, how the landscape is affecting the risk associated with wildfires, and then obviously all of that against the backdrop of a changing climate. And so we've been working on this for about 4 years now. Other partners in this include some of the folks at Google.org and Google Research, as well as the Moore Foundation, which has a big initiative around wildfire. And the ultimate goal is to deploy a 50 satellite constellation that is very much targeted at this wildfire problem. And we spent hundreds of hours working with stakeholders across fire agencies, climate and fire modeling scientists, a bunch of the land managers, the folks that are responsible for doing things like forest management, to really understand, again, what the key problems were in the space and what you could do from a space-based remote sensing perspective to put a big dent in it. And what we arrived at is essentially this 50 satellite constellation, which will provide both things like fire managers like CAL FIRE, CAL OES, near real-time situational awareness on new fire starts, but also, and I think maybe more importantly, as a fire is burning and they're trying to manage it and provision resources, something like 20-minute updates through the entire life cycle of the fire at sort of a resolution and fidelity that has been completely unprecedented in the history of space systems. And so it's not just an incremental step in terms of their ability to understand what's happening and manage it. We think it's an order of magnitude or a couple of orders of magnitude improvement. And so we launched the first satellite, what we call Protoflight, in March. And again, I think this is a really good kind of case study of our approach. You know, the traditional way to solve this problem would have been to go through a formulation process, come up with a set of requirements, and then 10 years later start deploying the satellites. Once we knew what this system ultimately needed to look like, we went from that to having a first satellite in space that was demonstrating the data we'd collect in about 15 months. This is, you know, completely unprecedented from the perspective of most large organizations that would be deploying satellites like this. And what that affords us to do is learn a lot very rapidly in ways that you can't do on the more traditional approach. And so the satellite's now been in space for about 4 months. It's producing data. We're learning a ton from the data. We're very happy to report that the data looks fantastic. But we're also getting to do a lot of things very early in the overall life cycle of this mission that normally you'd never get to do, like sharing data with the downstream users and customers that are ultimately going to be incorporating this into their operations. Typically, that wouldn't even start until many, many years later when the satellites are really getting deployed. And often that's the gating item. It's that getting data out the last mile to operators and first responders that prevents the uptake of these systems. And so we're really excited that this approach has not only allowed us to prove out the technology, which it's doing very effectively, but it's also allowing us to really get data in the hands of people that are ultimately going to be consuming it and learn from that process so we can incorporate that as we continue to scale it out. And I have a simulation here that I think just viscerally really shows the impact that a system like this can have. So this is a simulation of a fire propagating against the landscape kind of from above. And you can think about this upper left quadrant as temperature. So it's kind of like the thermal signature of a fire moving in the landscape. And then the bottom two panes here we're simulating. There are existing satellites that are used for looking at fire. They're typically weather satellites that were designed for weather forecasting purposes and not really with fire in mind at all. And they all have significant constraints. And so this is two of the civil satellites that are currently being used for wildfire purposes. One's called VEERS. It's a polar orbiting set of instruments on our NOAA weather satellites. It updates about every 12 hours, and it has about a 400-meter resolution. The other one is GOES, which is a geosynchronous satellite also used for weather forecasting, which updates much more frequently, but the resolution's about 1 kilometer. In this case, for this simulation, the simulation doesn't even go 12 hours, so we just showed an update on VEERS, so you see something. But what you very clearly see is if you're on the ground trying to understand where is this fire, how hot is it, where is it moving, ideally catch it when it's small before it's gotten big and out of control. This satellite data is almost useless, and that's the recurring theme you hear when you talk to first responders. The upper right pane is a simulation of what the FireSat constellation will see. And again, if you kind of put yourself in the seat of somebody that's trying to make decisions about where do I put resources, is this on this side of the highway or that side of the highway, where should I evacuate houses? This is really a transformational view into what's happening on the ground. So we're really excited about that. And then I just have some cool eye candy, and I'll try and get through this and then answer questions if folks have questions. So this is some more integration pictures of FireSat, the first FireSat before we launched it in our facility in Mountain View. It's a little bit hard to see, but the red piece kind of tucked in the back is covering the aperture of the fire instrument. A lot of the rest of the stuff on here is antennas and the solar arrays before deployment. This is a picture, a little bit more of a close-up of the actual camera on that satellite and the satellites that will come later. And again, this is something that was critical to enabling the mission that did not exist in the world, and so we had to take on at MUON developing this instrument as well as a satellite. This is just a cool picture of our solar array deployment testing before we actually sent it to space. And then I have some data, and so this is some of the earliest data. We released this publicly about a month ago from that first satellite. And you know, aside from the fact that there's all kinds of cool things you can see in this thermal infrared data, things like the fact that the runway in Sydney is warmer than the bay, and that you can actually see gradations in the temperature of the bay. The more exciting stuff is really when we started taking pictures of fire. And so this is a fire in Australia, a bushfire that we captured early on. And I unfortunately don't have a good comparison with some of the existing satellite systems, but you can probably imagine from that simulation what they would look like. And what we're seeing is incredible fidelity and sort of the resolution, the sensitivity to very small patches burning. If you look carefully in these images, you can see these very small, cool spots very clearly in the data, which is very important for fire managers making decisions. And you can also see, you know, how we very carefully selected a few of the spectral bands for this mission with fire in mind, and so fire shows up very prominently, specifically in this kind of blue-green picture, which is the mid-wave infrared band. We also got lucky and caught some very small fires. So this was a really exciting kind of demonstration of just how capable this system is. This was a small roadside fire in Oregon, and we actually got pictures from the local responders that responded to this, and we think this was about a quarter-acre fire, very, very small. We caught it right after it started when we flew over. And the interesting thing about this is there was 911 reports, and the first responders went out and put out the fire. But there's a set of other satellite systems, the civil systems, and then a set of other ones that are not discussed often, that we're fairly certain nobody else saw this fire. So it's a very good demonstration of just how this, focus on really optimizing a mission for a particular use case can develop something that is very powerful for that use case. And that's my talk. I hopefully went through that fast enough, and if there's time, I can take a few questions. Any questions? Yes.
Hello. Hi, Johnny. I'm Christopher. I'm a third year here at UC Berkeley studying electrical engineering and computer science. And my question to you is, since Muon's strength is in data, which industries do you see Muon injecting itself into? And then what are the plans to scale in those industries, like with data analytics for the consumers? And where do you see this going?
Yeah, I mean, we definitely have a lot of strength in data, and I think that comes in a few different forms. I mean, one is remote sensing, the collection of data. I think it's also in the movement of data. We've really architected our system in a way that's very good at moving bits around. And so, I mean, I think our primary focus today and for the foreseeable future is going to be on things like these high-performance remote sensing missions, communications missions, things where you're trying to collect either photons or bits and translate them and then move them around various places. In terms of industries, I mean, it's interesting right now. So our customers span, we have a bunch of commercial customers. We have Earth Fire Alliance is essentially a nonprofit customer, and then we also have government customers. On the commercial side, I think long-term, there's a huge untapped potential around remote sensing that just largely because of the barriers to entry, has never really been crossed. And one way to think about this is, historically there's been a small number of types of data collected from space, things like visible imagery. Now there's commercially available radar imagery, things like that. And those have applicability to certain problems. If you want to, see where cars are, high-resolution visible imagery is good. There's certain things you can help with that data, like some of it's used for agriculture a little bit, but it's usually kind of a secondary thing. And so I think one of the problems historically with remote sensing particularly has been that because it's so hard and so expensive and takes so long to get satellites into space, you try and build things to solve the general problem. You try and build satellites that can collect some data that hopefully have 100 applications. And I think that's very hard to do, and it has often not borne out that really moves the needle very much in any one of those applications. Where I think we're entering a place now where the barriers of entry have come down enough where you can say, for this particular application, if I want to improve crop yields, what's the most important type of data that I could collect to do that, to help farmers do better planting or water management or whatever? And then you can actually, it's affordable to go build a system dedicated to that, launch it, and operate it. And I think that's a really fundamental paradigm shift in terms of how you think about some of these remote sensing missions that we're now on the cusp of being able to do. So I don't know if I perfectly answered your question, but that's some thoughts about it.
Oh yeah, that was great. Thank you.
Other questions? Yeah.
Hello? I'm not going to say my name because I don't want to get in trouble. Given what's happening in the government right now, where they're shutting down NOAA satellites, despite the fact that it's still working, do you foresee a scenario where Muon's FireSat's constellation will be like the only constellation standing that can offer this kind of fire detection? And after this administration's over, like do you see this as being a dominant thing, or you know what I mean?
Yeah, no, it's a very good question. We've been thinking a lot about it. I mean, I think that, so I think there's a lot of different dimensions to the question. So one dimension is, historically, the government has built these satellites basically for the public good, for things like weather forecasting, that seems like, at least for now, are starting to go away. Can industry step in some way to fill that void? And I think there will be places where that is the case. I think FireSat is hopefully a good example of a place that industry and philanthropy and other things are stepping in. I think the other part of the question is sort of one of the problems with a lot of the systems that are now getting deprecated and shut down is they were developed in this paradigm of billion-dollar systems that take a decade plus to develop and deploy. And each new one, replacing one of those, is another billion-dollar project. And I think what a lot of the trends in space going on right now enable are more leverage of the commercial sector to help make this less of a huge burden for the government. So the government doesn't have to spend in increments of $1 billion. They can spend in increments of $5 million or $10 million to get what they need. And also just that the timelines, the rate of new technology injection to these systems can be much, much faster. And I think that'll, over time, completely change how we think about the paradigm of these type of satellites, the things like science and earth science and weather satellites, how they get built, how they get deployed. I think the government still has to have a part in that because there's some amount of that is public good and will never go away. But I also think there is some truth to the fact that the old model was somewhat broken and needs to get kind of repaired. So I don't know if I perfectly answered your question, but those are some thoughts. Yep.
Given that Muon Space is, a lot of it is the businesses like collecting data for customers, how do you see like artificial intelligence and cloud computing coming into play with your business?
Yeah, that's a great question. So I mean, one of the kind of core theses for when we started the company was actually that, this was 4.5 years ago and the world's changed a lot since then, but you look at the things that were happening in AI and the common denominator is that you need massive amounts of data to train these models to go do useful things. And they're incredibly powerful, and we believe that they were going to get more and more powerful, which has absolutely been true in the time the company's been around. But if that's the case and these models go and replace a lot of other ways of doing things and solve a lot of problems that have previously not been solved, what's going to enable that one layer down is the data that's powering the models themselves. And so we saw that as a huge opportunity. Again, it kind of goes back a little bit again to what could really unleash things like remote sensing data in the world. I think the trends in AI right now could really unleash that. And we're seeing this, for instance, I don't know how much y'all followed this, but Google a month or so ago announced that they're training what they call these Earth Foundation models, which are basically taking large-scale remote sensing, largely satellite data, and building foundation models out of them that are really meant to solve general-purpose problems or questions in a unified way, rather than having a bunch of different bespoke models. And I think that as that trend continues, there's going to be a near insatiable appetite for not only more data, but different types of data. And many of those types of data are going to need to come from space. Other questions? Cool. Thank you all.
So yeah, thank you so much to Johnny and Muon Space for that amazing spotlight speech. We do have a small gift as a token of our appreciation for coming and speaking to us today. We could get a quick picture. Melissa. And yeah, as we wrap up this section of the symposium, I want to say a huge thank you to our sponsors, specifically to Redwire and Astrolab for sponsoring the sections before this, and Muon Space for sponsoring the networking session after the lunch that is happening right now. So yeah, thank you.